Hello, Assalamu alaikum everyone. I hope you're all very well, healthy, and safe. So, welcome to the second lecture of this online learning for maintenance engineering. I am assuming that everyone have had the chance to go through the first lecture that I have uploaded on the Google Classroom under the lectures. And today what I aim to do is to make further progress from where we've left and build a few more concepts in defining and understanding the terminologies of maintenance engineering. So naturally I'm gonna have a recap of what we have discussed previously and then make my way towards expanding more into the terminologies. And of course, today I would like to then relate these terminologies and drop them down to uh, have a backdrop into, for example, types of maintenance and discuss uh, in, in, in what scenarios we might be looking at approaching different maintenance techniques and what are these overall techniques that are available to maintenance engineers, for example. So here is my slide set that I've discussed last time. We started off by looking at a true definition of maintenance engineering. We clearly deal with systems, right? And we, of course, deal with functions within the systems. And of course, we only deal with them in maintenance context when we have a clear cost benefit assumed. So there has to be a very strong narrative and business case for investing any sort of maintenance effort in, in maintaining the functionality of a given system, right? So for example, you wouldn't invest on a bicycle maintaining, for example, the brakes more than you could afford on a cycle. If the bicycle is only cost 10,000 rupees, you wouldn't adopt an approach of maintaining, for example, the brakes on it or the tires, which could lead you to spend, over 15 or 20,000 rupees. You might just go and buy a new one. Right? So that's what I mean by having a high value asset. We invest in things for maintenance where we see value coming out of our investment. Okay, and how we do that, of course, is through strategies, approaches of maintenance, which we will explore throughout the remaining course, and I will touch upon them today as well. And what we are really aiming for is maximizing the utilization of the system for a given purpose that is built for, right? So for example, a boiler is built for heat transfer, right? Heat transfer between hot and cold fluid. Now of course, heat exchanger over the time can degrade, right? It can degrade, it can get fouled, for example, or the channels can get blocked, for example. Now of course, what we want to do as maintenance engineers, we want to maximize, right? We want to maximize the utilization of the heat exchanger to the best of its functionality. So let's say the heat exchanger was designed with effectiveness of 75% of the heat transfer from hot to cold. Now we would want to make sure that it operates for its lifetime, let's say 10 years, at that 75% effectiveness. Okay, and we will adopt different techniques and approaches to maintain it. And The thing I want to expand on today is the relationship between maintaining it and adopting an approach. So really understanding what can go wrong with a heat exchanger, for example, right? Or what can go wrong with, for example, a bearing on a wind turbine gearbox. What are the fault modes? How do we really understand the fault modes, right? And how does fault mode relate to a failure, for example? And how does these concepts relate to maintenance and adopting a strategy that can enable efficient and effective maintenance maintenance methodology or maintenance approach. Okay, so we talked about system being complex. Every system we build are complex, so we have to appreciate the complexity of systems we're dealing with. Systems are comprising of subsystems, and those subsystems may also have their own subsystems. So for example, the motherboard on your laptop is a subsystem of the overall system, which is laptop, right? But motherboard again has other subsystems. I mean, subsystem, like transistors, um, and array gates, and resistors, for example. Those are also part of a system. Okay, so we really need to understand the whole hierarchy of the system and really break it down from system level to subsystem level to subsystems, subsystem, and component. Okay, let's say for an aircraft, for example, aircraft comprises of hundreds of different subsystems. So navigation system, surveillance systems, radar systems, fuel system, engines, auxiliary power. You have pneumatic system, flight control systems. All these are systems, but then within those systems you have subsystems and subsystems of subsystem. So a fuel system is a subsystem. Then in a fuel system, what you have is, for example, fuel tanks, right? Those fuel tanks are coupled with, for example, ducts, and, for example, pumps, right? You will have fuel filters in them in the fuel system as well. You will also have, for example, things like nozzles, spark plugs, so on and so forth. You have valves, control valves. So all those are basically subsystems. And what are components? So component would be, for example, the filter. And within the filter, you have those, for example, the techniques that I use to build those filters. So a filter could be, for example, a very high efficient particulate filter, or it could be a filter that is used for solid particles, right? There could be filters that are used for example, aerosols. Okay, so valves, for example, there could be a butterfly type valve. So the valve component here is, for example, the angular change of the plate. That is component level. The valve itself is subsystem because it's part of the fuel system, and the fuel system is a subsystem there. Okay, so what I'm trying to say is we have to have, as engineers, a systematic understanding of the system we deal with. Okay, and we have to really understand fault modes related with each subsystem, and then each subsystem's subsystem, and each component. And the reason why we do this is because we really want to understand how does these fault mode influence the functionality of the overall system. So let's say from the fuel tank, fuel is supplied to the engines. It has to pass through pump, it has to pass through ducts, it has to pass through filters, it has to pass through valves. Now, the reason why the engine may suffer lack of enough supply of fuel could be related to, for example, blockage of the filter. It could be due to the malfunction of the valve, which can be related to electrical failure. So if the valve is electrically powered, it may be that a circuit failure can lead to malfunction of the valve, and the valve gets stuck at one position, and so therefore we can't have enough orifice through the duct to supply enough mass flow to the engine. Okay, or it could be a leakage in the pipe, right? Or it could be that the pump that we are using is degraded as such that it is fouled, so it is not able to pump the flow sufficiently. So the reason behind why the engine is suffering lack of fuel flow can be related to multiple fault modes, and those fault modes are related to the subsystem's subsystem, and they can also be related to component level. Okay, so the functionality of the fuel system supplying fuel to the engine can be influenced due to subsystem level failures in this case. Okay, and this remains the case for all the system that we deal with. So system, the hierarchy of the system must be understood and laid out. Okay, we must understand the functionality of this system and how this functionality is influenced throughout the subsystems hierarchy. We then need to really understand at subsystem and component level what are the all ways it can fail. What are the ways that these systems components can fail that will influence the overall functionality of the system. We really need to list each and every fault mode for each subsystem and their respective subsystem and their components. And then we can start to think about how we can manage these fault modes. So how do we manage blockage in filter on a fuel system? How can we avoid that to happen? How can I avoid not having a malfunction in my valve, for example? Okay. How can I avoid having a leakage in my pipe, in ducts, for example? How can I avoid having deposition of, for example, solid layers in the inner surface of the pipes where the fuel is flowing? We've studied in fluid mechanics that in order for the flow to remain laminar and steady, we need to have smooth inner surfaces in the pipe. So if, for example, over the time the particles start to accumulate on the inner surface of the pipe, it will start to build friction, and therefore the flow can be influenced within the pipe. It can lead to increase in pressure drop across the ducts. Right? So how can we better manage that, for example? And only then we can then start to formulate an approach which enables us to address these fault modes, so we maintain the functionality and therefore we are able to maintain maximum availability of the system, so therefore we can use it as much. We don't have to shut down the fuel system to fix it, because we are now, for example, taking proactive and organized and well thought out approaches to maintain it. and therefore we can maintain the fuel system in a healthy operation and use it as much as we can. If you think about it, if we address all the fault modes, we are really saying that we understand our system in the ways it can fail. And look, this is how we will address them. So the reliability aspect of the system increases. Okay, less failures. As you know, I will go on to how fault mode, for example, is linked with failure of so the fault mode of a filter getting blocked due to presence of foreign particles in the flow. How does that fault mode, the blockage of filter, which is a fault mode, lead to failure of the filter? Okay, so reliability is increased by understanding the fault modes. By having a good understanding and high reliability, we can make the system available to do the function. And by having these two, what we have done is we have laid out a plan of maintainability. Okay? We have laid out concisely what needs to be done for which fault mode. If this happens, this is what you need to do. So the maintainability of the system is well understood. Okay, like for example, the fuel system suddenly fails. You already have in place diagnostics for the system. So this means maintainability. How quickly you can recover a system to go back to its functional state is called maintainability. Okay. And all these three are basically coupled together. High reliability will give you higher availability, and high availability can only be achieved when you have high maintainability for a system. Okay. And of course, the whole reason why we do this is because we want to be able to, for example, in the fuel system context, we don't want the fuel system to fail and stop supplying fuel to the engine. Because in this scenario, what will happen is that the aircraft cannot fly. And if the aircraft cannot fly, I cannot take passengers, right, from A to B. My whole business is dependent on making the aircraft available for its functional state. So if I have high reliability, high availability, high maintainability, I am maximizing utilization, so therefore I can maximize my revenue. More the revenue, the greater the profit margin will be. Okay. And of course, it's very strongly coupled with safety as well. If you really understand how different subsystems will fail on your system, you are really addressing the safety aspect of those systems as well. You're not leading to a situation where you're jeopardizing the safety of your system failing catastrophically. Okay. Moving on, and I want to here basically look at more closely how a fault mode leads to failure. Here I have chosen, for example, a simple illustration of a wind turbine gear assembly. Okay, so this thing holds, for example, the wind blades, wind turbine assembly, and spins it. And let's say that these bearings, let's say these are uniquely designed advanced bearings, and these bearings are obviously housed. This is the housing of the bearing, and these are the bearing itself. These bearings allow the rotational speed to be at, for example, natural frequency, and it avoids high vibrations. It keeps it stable, for example, overall structural integrity. So let's say that design speed of these bearings is at 20,000 RPM, revolutions per minute. Okay? So these bearings spin at 20,000 RPM. They're made of, for example, alloy, and they are very strongly coupled with the neighboring components, and formed in a housing with sufficient supply of lubrication for that RPM, and they are designed as such that it's meant to be maintenance free for example 10 years. When I say maintenance free, is that you provide it with just right conditions within. So for example, let's think about this bearing is deployed in wind turbine, and this wind turbine is installed on a mountain in Swat. The external conditions throughout the seasons can vary from, for example, -10 to plus 30 degrees Celsius. The wind speeds on this gearbox, which is in an assembly, of course, there's a housing outside as well, are, for example, from 30 meter per second until 60 meter per second. So how many ways can this bearing fail? Well, the very first thing that can happen is, due to the high RPM and the torque and the torsional stresses and the normal stresses acting upon this bearing, it is likely that this bearing can start to have structural damage. And very common failures with bearings are, for example, initiation of cracks. Okay, so this guy is now experiencing, for example, lack of lubrication after 1 year, and it starts to experience more friction, like metal to metal friction with the neighboring components because of lack of lubrication. And so what it leads to is what we call crack initiation. So this crack initiation will obviously expand the volume of this small bearing, and that can lead to, for example, a natural frequency that is above the natural frequency of the overall housing. Okay, and those can lead to cause intolerable vibrations. Okay, this crack, for example, that has appeared on the bearing, if this continues to operate in the same conditions, can very likely increase over time and effectively lead to breaking this bearing. Okay, so what is fault mode here? Fault mode here is, effectively, if this fails, then this whole housing will suffer significant vibrations, and due to that it will be unstable, and it can lead to basically rupture. This whole thing can collapse. The failure mode here for the bearing is not lack of lubrication. The failure mode here is structural damage in terms of crack initiation. Okay, we have failed to provide the bearing the right conditions, lubrication conditions, for example. It has led to increase in metal friction of the bearing, which has gone beyond the structural, the material integrity of the bearing we have selected, and therefore it has led to damage and initiation of crack. And that initiation of crack over time leads to the fact that this breaks and the whole thing dynamics are impacted, and this gearbox basically stop working. Okay, now note that when this lubrication is less than required, what happens that the metal to metal friction comes in. This metal to metal friction causes stresses. This stresses causes crack. Now, while the crack is in place, the bearing is still working. The bearing is still doing its function. The gearbox is still doing its function. It only when the crack reaches a certain level of length or severity, the bearing is basically broke, or the bearing gets rupture, and that stage leads to significant instability due to high vibration, and the whole gearbox stops working. That's where the functional failure comes in. Okay, so having a fault mode does not mean that there is a failure. Okay, a fault mode is always related with severity. Okay, somebody says and tells you there is a crack in the bearing. Well, the first question you will ask is how big is the crack? Where is the crack, right? What's the location of the crack? What's the rate at which it is growing? What's the severity of the crack? Okay, having a crack does not mean there is a failure. A crack is a fault mode in a bearing, for example. Just like a blockage of filter is a fault mode. Filter will always work, but it just won't work as efficiently. It will, of course, completely stop working once the blockage leads to a specific severity. Okay. So here I have drawn how, for example, we can put this in words and understand the journey of fault mode leading to a failure. I'm going to use another example here. Okay, imagine you have a gas turbine, right? In a power generation plant, you have a gas turbine, or we can even talk about, for example, the hydro power station having those Francis type turbines, which effectively have rotating machinery, and they have, for example, blades that are used to create potential flow in fluids, and therefore we achieve through that potential flow kinetic energy and convert it into mechanical energy. So let's say the blade is experiencing deposition of foreign particles coming in the fluid. As you saw when you visited, for example, Barotha dam, the water supply coming into the dam was fully exposed to the environment. Okay, of course they were employing different filtration techniques to ensure that the water is purified and is not contaminated when it is supplied to the turbine. So still at microscopic level, those turbine blades can suffer deposition of foreign particles onto their surface, and with time what happens is those particles form a solid layer onto the blades. Okay, we call it normally fouling of blades. Okay, and the fouling of blade basically influences how the flow behaves over the blade. It effectively impacts how much energy you can extract from the fluid, which is in this case water. So the fault mode here is what? Fouling. Fouling is fault mode. Now this fouling have certain severity level. The deposition of foreign particles will form a solid layer, and this layer will increase in thickness over time on the blade surface. The increase in length of that solid layer due to particles accumulation is what we call degradation. Okay. This blade is now degraded. even if the length is 1 millimeter of the layer of particles, the blade has started to degrade. Okay, and let's say when the blade was designed, the designer said this blade can only afford, for example, 10 millimeters of solid particles layer. So you can't afford to have more than 5 millimeter of solid layer on that blade due to foreign particles. If you reach that limit, what will happen is your blade will basically not extract any energy from the fluid. You know what does turbines do? They extract energy from the fluid, right? So fault mode is accumulation of foreign particles, and we call it fouling. This fouling degradation occurs when even 0.01 millimeter of solid layer starts to form, and this degradation is strongly related with severity. So over the time, this layer will increase. It will go up to 1 millimeter, it will go up to 2 millimeter, it will go up to 3 millimeter, and the severity of this degradation will increase. Okay, so, and this severity will effectively lead to severity that we have designed as design tolerance, which is, let's say, 5 millimeter for the wind turbine blade. And once that happens, the blade fails to extract any energy from the fluid, and we don't get any expansion from the flow. And at that stage, the function of the turbine is no longer available. The turbine is not in functional state anymore. So taking example of my bearing in the gearbox, crack starts to initiate due to lack of lubrication. Let's say the design limit for the crack to this bearing to break was determined to be, in these conditions of rotation speed, was determined to be in this condition RPM, and given the lubrication of certain amount, this bearing can only sustain, for example, 10 millimeter of crack in any geometrical coordinate. Okay, so the crack here is fault mode. Once the crack occurs, the bearing is degraded. The crack increases, the degradation severity increases. Yeah? The growth of the crack rate. Okay. Now, once the crack occurs, degradation has started. How quickly the crack is growing is also part of severity. Okay. How quickly this crack starts to propagate through the bearing is part of also degradation severity. How big the crack is, how fast it's growing, what location it is at, all these are part of severity. Okay. Once that severity reaches my design tolerance threshold, the failure will occur. The failure will occur because the bearing is broken and the gearbox is not able to function anymore. Okay. And once that gearbox is not working, my wind turbine is not working. I'm not extracting any energy from the wind, which is the whole purpose of the wind turbine, to extract energy from the wind and convert it into mechanical power. Well, convert it into mechanical energy and electrical power through the generator. So it's very important to understand this slide here and this slide here for really building a baseline concept of maintenance in engineering, and the terminology and the criteria that we use to assess and examine maintenance. in engineering. Now, okay, we understood here that systems have subsystems and subsystems have their subsystems, and those subsystems have their components, and everything is driven by the very basic fact of fault modes leading to degradation, severity, design tolerances, failure, functional failure. Okay. In the next slide, I'm trying to basically capture how you reason fault mode, how you map the causation of fault mode. This crack was initiated, and we said, okay, it's lack of lubrication, the metal to metal contact has increased, stress is increases, it's still rotating at very high RPM, there are torsional forces, there are stresses presence in very high sensitive regions, and so therefore it has lead to forces essentially that has led to failure of this bearing. But we have to be very careful about how we cause a fault mode in a given system. Okay, and I'm gonna stick to this example. Fault mode in our case was given as initiation of crack. Okay, we noticed it, we observed a crack, let's say. How we observe the crack is another question. How do you know there's a crack on your bearing, for example? That's something else. Let's just assume that we've been given a report. We are head of maintenance engineering. Guys developed wind turbines and supports and operate them, and a report comes in that one of our turbine is showing crack in bearing. Now, how do you cause that? How can you trace and map the fault mode? Well, the very first thing you want to do is you want to ask the guy and analyze what's the material of this bearing being used. Is this bearing designed properly for those conditions it's operating in? That's the first thing you want to ask. That's the first thing you want to know. This bearing is made of alloy. Okay, is it steel? Is it titanium? Is it nickel? Is it copper? What is it made of? Then you want to know what kind of conditions is this operating. Oh, right, so the crack occurs when this bearing is operating at 20,000 RPM. But should you really be operating this bearing at 20,000 RPM when you have made it with a nickel alloy, for example? Or should you really be, you're really falling outside the limits of using nickel, and you should really be using titanium. What I'm trying to say is that you need to first pay attention to design flaws. Okay, is the bearing size appropriate? Okay, they've chose the right material, they've chose the right integrity of material that shows right integrity and properties for these conditions. It must be operated in these temperatures. It must be operated in. But has the bearing being designed with the right shape and size? And does it have the right weight to be operating at these RPMs to ensure its stability and dynamics? Okay, is the bearing okay? The bearing is even designed properly. Its shape is appropriate as well. But is the integration with the other neighboring system appropriate? How have you installed this bearing and coupled it with other bearings to form this whole annular bearing cross section? Is the integrity of this coupling system appropriate for operating in such high frequency environments? Okay. So we really have to pay attention to how the things are designed when we look at faults. It might be that this bearing is not even worth exploring or maintaining anymore because it's not even designed well. They have used the wrong material to design it. So you're not going to put any effort in maintaining it. You're just going to say replace it, right? Design a gearbox that is robust and satisfies the requirement of these operating conditions. The design has to be effective and efficient. You have to validate it and test it. The second thing is we have designed it right. Everything is processed well, but we haven't fabricated it well. The manufacturing part of it, we haven't used the right manufacturing techniques to manufacture these bearings. There are manufacturing faults in it. You said it should be this size, but it's not that size. When you ended up making it, the circular circumference was not, for example, 5 millimeter, but it's supposed to be 5 millimeter. But the manufacturing process that you have chosen has led to manufacturing residual errors in the bearing. Okay, we call it residual errors in manufacturing, leading to design shortfalls. Okay, so this block here is not using the appropriate and right manufacturing techniques and having residual errors through manufacturing processes, which leads to defects and therefore design flaws. Okay. The third one is, okay, we've designed it well. Manufacturer residual error is acceptable. It's within the range we have designed. It's within the tolerances of residual error. Everything that is designed in industry has some sort of manufacturing residual tolerance. Okay. Everything is fine in this region. Now we look at, okay, what is going on in the conditions? So it's supposed to operate at 20,000 RPM. We have to maintain an external temperature between plus 30 and minus 10. External winds of about plus 30 meter per second to 60 meter per second. What is different from these operating conditions? Is it the fact that we are operating this above 20,000 RPM? Or is it the fact that we have very high temperature in this region due to, for example, lack of lubrication? So, we're supposed to supply 5 liter of a specific type of lubricant yearly to this particular gearbox, but because we don't do that, it leads to frictional metal to metal friction, and that raises the temperature within this gearbox, and which leads to basically stresses and vibrations. So the operating environment within the gearbox and externally to the gearbox, okay, things like there is very cold conditions, so icy conditions, what can they do? They can compromise the structural integrity of different alloys. Okay, what we call the cyclic effect of external atmosphere. Okay, mostly referred to as corrosion and erosion. Here in internal operating environment, lack of lubrication will lead to, for example, metal to metal friction. It can cause stresses, high temperatures, and usually these kinds of stresses are cyclic in nature. The cyclic temperature variation, and mostly referred to as fatigue cycles of different metals and bearings. Or it is likely that the fault mode, the crack, is occurring because of a synergistic consequence of all these three things. Mostly you would want to then, in this case, say, right, design is not properly done, there is high residual manufacturing error, and the operating conditions are not as what this thing is designed for. So the whole thing is messed up in this case, right? You would be very much tolerant and say, look, the fact that this crack is occurring because this thing is now operating in high stress environment, and that is usually because there is lack of lubrication, so we need to just provide more lubrication to it. But if you find out that it's because this thing is not designed properly, this is a much major concern. Here you may provide some more lubrication, and perhaps you can address its stable operation. But if the thing is not designed properly, or there's very high manufacturing error, then you would have to completely replace that. So the causation, how you put a rationale behind your fault mode from an engineering point of view, how you go and explore the root cause of something that has occurred. So this is not failure, this is fault mode. Okay, fault mode causation. Yeah, so for example, in this simple scenario, what we are looking at is, let's say everything is fine in terms of design, manufacturing, but we notice some concerns over operating environment temperatures. We notice high vibrations, and the data suggests that the gearbox is suffering from high temperatures and high vibrations. So the first thing you will say is you want to maybe lubricate this every year, every 6 months. It depends on many factors, but what the category this kind of maintenance falls in is called preventive maintenance. Okay, so we have a plan of doing a regular check and doing sufficient measures and taking appropriate actions to ensure that the functionality of this gearbox is maintained. So maybe I want to just duplicate this every 6 months, and it doesn't give me any major concerns depending on the data that I collect. Okay. So the fault mode causation will give you that knowledge and understanding as to which way you should be going towards maintaining it. Okay, so there are a wide range of different techniques available in maintenance, and the next thing I want to do is to look at these different maintenance techniques. Okay. So here these slides are also available on your under the lecture portal on the Google Classroom. So we all understand maintenance objectives by now. It's about functionality, it's about maximizing usefulness of here I would like to call it system, not equipment, and maximize production capacity if you are in a factory, for example, minimize cost, minimize frequency of interruptions, so frequency at which the failure modes are occurring. I want to minimize the failures to occur, and therefore I can enhance safety of the system and the manpower, right? By ensuring a fully functional aircraft, for example, what you're doing, you're making the passengers to be safe and also the aircraft to fly safer, right? If the aircraft is safe, the passengers will be safe. If the aircraft suffers, passengers also suffer. Okay, so safety of the system and safety of the of the tangible assets that are associated with the system are correlated strongly. So these objectives you want to make yourself very clear and happy with. Importance of maintenance is substantial. We want to really understand all the ways our system can fail, identify cause of failure. Failure is due to design defect, where failure, all these things, just like I have discussed. Where are all these faults coming from, and what are all the faults, and where are all these faults really coming from? I really want to understand the root cause of it, okay, not just on the surface. I really want to understand the root cause of these faults, and then I can deal with them better. Different types of maintenance. Maintenance is simply of two types. There is a type of maintenance that you have prior knowledge about, so you can plan it, and there is a type of maintenance that is unforeseen. You have no idea about it. It just simply occurs without your knowledge. Okay, you have no idea that my system can even fail in this manner. Okay, maintenance is either planned or unplanned. So planned maintenance is nothing but scheduled maintenance, okay, and unplanned maintenance is what we call unscheduled maintenance. Right? In most industries, most of the problems engineering teams face are due to unscheduled maintenance. The overall cost of maintenance for a given company, let's say PIA, their maintenance cost is substantially influenced by unscheduled maintenance problems. There is a failure in the aircraft fuel system, and that failure is something that they don't have prior knowledge about. They cannot diagnose this. So if they cannot diagnose this, they will have to spend much more time sending it back to manufacturers, really asking them what is wrong with it. They will then look at through the engineering team and come back to them. So unscheduled maintenance lead to very high downtime of the aircraft, and that downtime is very costly. Okay, the cost of maintenance, remember, is never just putting a new lubrication or a bolt. It's also the time you spend by having your asset or system not available, because when you're doing maintenance on it, you're not utilizing it for its purpose, right? So that cost needs to be offset with maintenance cost. So planned maintenance is preventive maintenance, corrective maintenance, predictive maintenance. Preventive maintenance is more like lubrication. I lubricate my gearbox every 6 months. I, for example, provide sufficient means to address the vibrations and high temperatures due to metal-to-metal contact. Preventive maintenance can also be, for example, heat exchangers on air conditioning systems. So we wash the heat exchangers now and then to not have any blockage. So people do it on their cars every few months. You take your car and you wash the radiator, because it gives you better performance, because it eliminates all the blockage that has occurred in the radiator. So preventive maintenance is things that we do on a regular basis to address a specific fault mode, to ensure we have better efficiencies and maintain functionality at its best. This is not really addressing failures. This is addressing fault modes at a given degradation and severity, okay, and you enhance it to its better functional state. So you take preventive measures and reduce the severity level and the degradation of the subsystem. Corrective maintenance. Okay, so in preventive maintenance you have running maintenance. You can do things while the car is running. For example, you can only do preventive maintenance when it needs to shut down. So maybe you can wash your radiator while the car is running. Okay. When it rains, for example, when there's heavy rain, your car radiator gets washed as well, for example, in the front of the vehicle. When you want to do, for example, the spark plug change, you have to shut it down, right? So all these are scheduled maintenance. So scheduled maintenance is more of an mix of running and shutdown. So there are things you can do while it's running, and there are things you can do where you have to stop the system and do your maintenance actions. Corrective maintenance is when, let's say, the tire is punctured and you have to uh, fix the tire, put a new tire in. Here you're waiting for the fault to occur. Here you're waiting for the fault mode to lead to failure. Okay, so the tire has suffered a small minor damage, and this damage has led to tire getting punctured. So you waited until it's get punctured and you fixed it. Had you have fixed it while it was small crack on the surface, maybe it would not cost you as much. But because you have waited and it's gone quite severe and puncture, it may cost you much more money and time. Okay. And the corrective maintenance is also strongly related with the shutdown maintenance, where you have caused it to lead to failure as such that it's compromising the availability and running time of your system. Okay. Predictive maintenance is also a field. Here basically what we're saying is we examine the subsystem component in real time. So for example, in my bearing case, I have put, for example, here a accelerometer, and I have somehow installed here a thermocouple, and I am collecting real-time data through a data acquisition unit from the wind turbine, and collecting data and analyzing in real time if this accelerometer experiences vibrations more than the tolerance of this gearbox, or this bearing inner housing suffers temperatures more than I should be expecting, and then I can swiftly do something about it. Okay, so that's called predictive maintenance, which is based on collecting real-time data from the subsystem components that provides you the indication of health state of that subsystem. Unplanned maintenance is this bearing on the gearbox is failed because of things that you didn't expect. So it could be that a very unexpected climate condition, tufan has come or typhoon has come, and this caused a very high stress on the wind turbine, and it has led to basically catastrophic failure. Okay. Unplanned maintenance is all about failure modes that we have no knowledge of. Okay. So for example, taking the aircraft fuel system, the filter can in the fuel system can fail because of, for example, a blockage, a fouling, but it could also fail because of reasons that we don't know. One example could be that there is a sudden malfunction due to electrical component failure that powers the flow in the fuel system. So we might be expecting that it's is the filter or the valve causing the blockage, but it could be completely different, okay, of nature. So all these fault modes have been defined here. You can go through them, and if you have any questions, let me know. But I have already been through most of them. Okay. So have a look at those, and we will continue from there in more detail next time. Okay. So here there is a procedure for preventive maintenance. How do you systematically plan your preventive schedule maintenance, step by step. Uh, so have a look at those. But really, what I want you to understand is the journey of going from basic fundamental conceptual understanding of maintenance engineering. I really want you to understand what you should think like as a maintenance engineer. Okay, what are you should be really focusing on? Look at the bigger picture. Understand the root causes, how internal design conditions, variables, external atmosphere, design flaws, manufacturing flaws can relate to fault mode, and how fault mode is related to failure. All these points needs to be very well understood for grabbing a solid understanding of maintenance techniques that we will explore later on in the course, perhaps after the midterm. But for now, I think that's all from me, and I hope you're finding this online journey quite useful. And if you have any questions, let me know. You have the assignment due for 15th of May. Ghayur, I am expecting you to send me all the assignments, collect them from students, and Ibrahim as well. Please collect all the assignments and send them to me on 16th of May. So with that, I wish you good luck, and take care and stay safe, and speak next time. Allah Hafiz.